Morning. Well, first of all, I'd like to thank Pablo for the opportunity to come here and present this work. It's always a pleasure to come to Argentina, so I really enjoy Buenos Aires and also all the excitement that that I was able to see here yesterday. I didn't realize that there were so many people working in this field, so for me it's very, very gratifying. So right now I'm going to be showing some of the work that I've done with the team at HP. Okay, so there I worked in a position to help people, guide and direct a little bit of their work, and I very rarely involved to lab activities. So I'll make a note if there's something here that I've done. So you see, I didn't do a whole lot. So basically, this belongs to all the people that work with me. And more recently, I left HP and I moved to this company. It's a semiconductor foundry company that was started in Porto Alegre recently. So this is basically what I'm going to be showing you, which is the fact that, as you already saw yesterday, there's some very interesting scientific and business opportunities for people to work in this area. I hope I'll be able to convince you of that. Okay, well, the first thing is what is called this data explosion. And this is driven primarily because of all the different types of things that people are doing these days concerning data. People want to put the data in so-called cloud or whatever they call it these days. And this is something that was very interestingly noted by Marissa Mayer, who used to be at Google. Now she's the CEO of Yahoo. And what she observed was this, that the storage needs actually grow faster than Moore's law. So, I mean, what's interesting about that is it's not the fact that, the obvious consequence is that things have to grow bigger, right? Even though you can make the storage devices smaller because of Moore's law, you're still going to need more space to store all the data that it's creating, or you're just going to have to sell more. So this is a very interesting opportunity, and this trend does not take into account the so-called Internet of Things, right? So this is a term that has been coined and people are using more and more, but this is basically the ability of things actually interact with the Internet, right? So, just get a bottle of water and then somehow it interacts. So the company that I work for now, they make RFID, so radio frequency identifiers. So that's a very small baby step towards that type of vision. So the lesson that we learn here is that you want to be able to work and understand non-volatile memory. That's the thing that you want to be able to do. The plot that I made here, I got this off of the web, really. I put it together. And this I got from the ITRS map and the projections. And this here I got from, a free report that was online on the usage of storage, but storage in hard disks. But you can create similar types of trends for any type of memory, whether you're talking about storage or memory. Storage class, people usually say non-volatile or situations in which latency is not a big issue. Basically, you're filing away your stuff. It's nothing that you want to read every second or every millisecond. So, so magnetic storage, as you can see here, even though there's this, it's a little bit archaic technology, right? I mean, I find this very interesting. But you see, nothing changed a whole lot. That people just made this thing here smaller, but it's the basic, it's basically the same thing. This is a hard disk that is probably spinning around inside my computer. The difference is that it's much smaller, right? But you still have the same things, and yet it's still growing at this 60% a year compound growth rate. So, but this is cool. Maybe this is like a 1 kilobyte or something like that. I don't know. So I'm sorry. Okay. So what is happening more recently, it's like over the last 4 years or so, 5 years, is that people are starting to use flash memory, you know, the pen drive, thumb drive, depending on who you buy it from. People are starting to use that in a so-called all-silicon systems. And here I just put three examples. One of them is, this is a relatively recent company in the Bay Area. They make, you know, racks of flash memory for servers. This is the market that these guys are chasing, right? Fusion.io was founded, it's a company in Utah, was founded, I mean, not founded, but Steve Wozniak is part of it. Okay, so one of the founders of Apple is the CTO of this company. So he saw the opportunity as well. Apple is the largest consumer in the world of flash memory. And also TI had also their offering here. So there are other companies that have similar types of systems, and this thing is just exploding. Just to give you an idea, there's an Israeli company earlier this year, the name is Enobit, and Apple bought this company for $500 million. It's a company with, I don't know, maybe less than 20 people. The reason why they bought is because Enobit was working on flash cells, and they figured out a way, okay, doing error correction coding, they figured out a way to optimize it better. So since Apple is the largest consumer of flash memory in the world, they decided, you know, this is a very place to be at. So flash memory is a very, very interesting and compelling technology, and it's been doing, I mean, people have been doing that for the last 20 years and achieved its maturity state. But, I'm sorry, going back and forth. But the prospects are not that exciting, or they're a little bit grim. It's not that people are going to stop making, it's just that it's not, flash memory will not be able to keep up with the decreasing dimensions. And the reason is as follows. As you see here, as we're moving towards, you know, 40 nanometers, 30 nanometer, 20 nanometer types of technology nodes, what happens, and this is shown in this graph here, the different colors correspond to single level cell or multi-level cells. Multi-level cell in the flash community means 2 levels. Okay, it's funny that they call multi-level. It's only 2 levels. So the thing is, this here that is dropping. Okay, this is the endurance. Okay, how many cycles depending on the lithography node. And this I got from Micron. So they are one of the manufacturers. Okay, so this is what they're saying, and the others, when they show something similar. So as you shrink the device size, then the device just starts dying sooner. And this is for the single level cell. This one is for the multi-level cell. And now here, this is the ECC, error correction coding, on the left side here, or the right side, that the need for that just keeps on increasing because you're going to make mistakes. Devices are getting so small that you're going to have to pay a premium, have to add redundancy in the system to compensate for that. So this is the message here, is that things are not looking very good. So what this is calling for, apologies, is there's a demand for non-volatile, scalable, you want to be able to scale, resilient, high bandwidth, because it doesn't matter if you have a big, system like a hard disk with terabytes of data. It doesn't matter because you can only get one bit at a time, because it's a very, very fine pipe that you're trying to suck all this lake of water, and it's a thin straw, right? You have to wait for the disk to go to make a turn.
Yesterday, people gave a talk that the way I heard him was that he said that flash is really getting better. He was a bit more optimistic than the picture you think. Do you want to comment on that?
I'm sorry, who said that?
People, he had his comparison slides.
Oh.
He somehow expressed a bit more optimism about.
Oh, too bad he's not here. But you see, that the thing is this is shown by Micron. And I can give you the physics. I'm just showing this, but let me give you the physics. What happens is this. You make your tunnel barrier, right? Because it's a floating gate memory. You make your tunnel barrier small as you shrink the device size. After a while, maybe people figure out a way of actually taking care of endurance. But the problem is not that. Then if you figure out that problem, the other obvious problem is retention. Because you make the tunnel barrier thinner, then you put an electron, it's going to go away. So even if you make it perfect, okay, let's assume you make it perfect, you lose retention. So I don't think it has a future. So that's why we need that. And we need it to be cheap too. But cheap is not just cheap like flash cheap. It has to be much cheaper, like 10 times cheaper than that. So here I put some, this maybe answer a little bit of that. And of course, people from the magnetic community, the magnetism community, they usually don't like this. They say, no, there's a way to do that. So some words are still in Portuguese. So here is how do you store the data? You can store it as electron charge, a magnetic domain, a ferroelectric domain, and a crystal or amorphous phase. For example, what is shown in DVDs and CDs, and then you have PCRAM that he talked about, ions and atoms. I put that at the bottom here. And then maturity here. This is all mature, and then you have all these size limits here. SRAM cells, he talked a little bit about SRAM. Basically, that's what you have in your cache next to your processor. If you get a picture of a processor, you're going to see that between 25 and 50% of the area in a processor is devoted to SRAM cell. Why is that? You need all your registers and things like that. And the simplest SRAM cell requires 6 transistors. So 6 transistors is really big. It's very, very big. And it's static, right? It means that it's always drawing power, so you can keep that, state there. If you're able to make any of these here non-volatile, these are volatile. If you could make them non-volatile, that would be basically a revolution. So that's why I think there are many, interesting opportunities here. So STT-RAM is one of the techniques that people are considering, and he talked about that for replacing DRAM and SRAM. So these are some of the limiting factors, and this is maturity in terms of being able to manufacture some of these. So as I put some caution marks here for these two, which are the ones that seem to be promising, if you look at the sizes, and also because people have not yet shipped a product with this. Now, PCRAM, Samsung, I think they ship a product with it, but this is too power hungry. Yet there are very niche applications that people can use. At ferroelectric RAM, people sell products with this, but it's the problem is the size, and of course hard disk and MRAM. There's a couple of companies that actually are trying to sell some of these products. Okay, so this is basically what I'll try to cover. And I'm sorry I took a little bit longer than I thought. I'm just going to go over some of the definitions of a memristor. Then I'll talk a little bit about, oxide electronics, which is a very exciting field to be at. And I'll give you a little bit of, information why I think that is. So the key thing is this, and maybe in this community, a lot of people talk a lot about, say, a memristor, this and that, or resistive switching. So the one thing that we all have to keep straight, and from a understanding point of view, is this, and it's not like a sales pitch or trying to name something that already exists, but it's something very fundamental, and it comes from network theory from Leon Chua. So he postulated, and Chua is a double E guy, so he's an electrical engineer and he's a theoretician. And then he postulated that there should be another type of element that basically, because you cannot get all types of behaviors from just the 3 existing ones, like capacitor, resistor, and inductor. And he showed this is the type of curve, this hysteretic behavior. And the key point, and I don't want to get into the math because a lot of people get hung up on that, myself included. So, but just looking from an experimental point of view, you just look at these different curves here. These, this IV traces as a function of time. There's no way you can make a combination of these 3 elements to obtain a curve that looks like this. It's not possible. Okay, it is really not possible. And it's kind of like looking in a Hilbert space, in an orthogonal direction. They form a base, but this does not belong to that base. Okay, so this is one way of looking at this. And therefore, he said, well, this is a fundamental element. So you have to include that if you want to do any circuit theory. So how do you make that? I'm not going to get into the details too much because we saw lots of examples yesterday, but I'm going to get back to the point of the crossbar as was illustrated in a few talks and why that is important. So let me just spend a little bit of time here. Why is it that people are working on that? So there are advantages. In oxide electronics, I'm talking about transition metal oxide, like a titanium, hafnium, tantalum. The key thing is this, it's the CMOS compatible for the most part. I mean, for all the ones that I mentioned, vanadium, even I'm not sure about vanadium, but niobium, many of these, they are compatible with CMOS. And this is a big thing because once you bring into a fab, if you bring gold or if you bring any other exotic material like iron or any like lead, I mean, who wants that in your fab? CMOS compatible, it means that if you're going to put something in your fab and it's not going to contaminate your front-end processes. Front-end are everything below the oxide, like a diffusion of species into the silicon, ion implantation, gate oxide, and all of these processes that are very, very delicate. You have like just a tiny bit of gold, and then it shorts your transistors because gold diffuses like crazy. That's why, for example, copper was such a big thing. Companies that developed, I mean, IBM was one of the companies that developed copper, and the reason why they did successfully, they almost have to have two different fabs, one adjacent to each other, and the one that dealt with copper, once you hand over the wafers that need to be, put this so-called back end of the line process, back end is basically what comes on top. But that wafer would never go back. And they had to build all sorts of diffusion barriers to make sure that all that copper wouldn't get into the circuit. So that's why people don't want to do that. One example that Kittel showed yesterday about silver, one of the products that is actually being offered by Adesto is actually made out of silver. It's a chalcogenide. And it's actually, he's selling. The big problem there is retention. Okay, so yeah, sorry I digress a little bit. So it's included this step as a back end of the line process. In other words, you finish everything you had to, and this is really exciting because what this means is this: anyone here in this room, of course, or in many places, can design a circuit. All right, can design a CMOS circuit, send it to, I don't know, TSMC. Bring it back and leave openings or things that we can actually build your own device there. Anyone can do that. And it's not crazy expensive. Why can you do that? Because you can incorporate these ideas as a back end of the line process. You don't have to have a $1 billion fab to try some of these ideas. You just have a small investment, maybe a few $1,000s, you get your wafer, and then you get a few chips. So for lab work, that's fine. For selling a product, it might not be, but then you scale and do other things. So the other thing is this is really an embodiment of three-dimensional chips. So Dima Strukov, so he had lots of different ideas how you can start stacking multiple layers of this and very, very clever schemes. And finally, it's a non-crystalline material. So you're not talking about epitaxy, which is an area that I worked for a number of years. I always get this backwards, sorry. So this is one of Dima's idea that I like to use to illustrate what back end of the line is, which is basically all this. See, this is something that we did while at HP. So this is, for example, one of those. Things here are big, okay? They're not small. They're about 150 nanometers or something. So this is considered big. But this demonstrates that you can actually do this process in a 300 millimeter wafer. Okay, so this is a zoom of one of the cells that we built at HP. So that's basically it. So this is the CMOS, and then you put everything on top. All right, so now I'm going to get a little bit into the specifics of the materials that we chose to utilize. One of them is tantalum oxide. So the number one feature that people like to address is this, endurance. And then maybe we have gone too far. We, meaning like the community, not only us, that we published this in 2010, we're able to get, I think 10 to the, I forgot, but I mean like a 10 to the 10, 10 to the 11 cycles. And then we stopped measuring. We should have gone further because it was still working. And then shortly after that, the guys at Samsung showed a couple of orders of magnitude. I don't have a slide here with me, but there's something very interesting about this here, and I regret I didn't bring, but I have a little movie that shows that we recorded while testing the device, because here you have 140 points. So what this tells you is that your bit error rate is better than 1%, but you cannot say that it's 0.1% or 10 to the minus whatever, 10 to the minus 25 or whatever that it's needed for a DRAM application. Here, but we're still working on this, we can show what the bit error rate is because we created a protocol and a infrastructure that we measure every single cycle. So bit error rate here is less than 1%, but it's measurable. So these are some of the things that we have. Just showing this, or just even showing this, is not enough. So there are lots of things for us to keep working on. So let me get a little bit started on this. So the number one feature we got was 10 to the 10 or 10 to the 12 cycles. So let's take a closer look into this. What kind of device do we have here? So the way to do that is by localizing, all right, the switching region, and then cutting with a focused ion beam, and then examining with EUs or whatever materials of choice, like a characterization of choice, like TEM and things like that. So this is basically what I want to describe in the next slides. So I keep having to do this. So this is how the technique works. So what you do is this. Let's imagine that you have a channel inside your device, and then you scan your tip on top of your surface, and then but you squeeze it. Okay. So as you're doing this, you monitor the conduction. So this was a work that was initiated by a former postdoc of Stan, and now she's a professor at UC Irvine. And Feng was her student, and then he came to HP, and then he's a very promising young scientist. He's now back in China, has his own gigantic lab with lots of people working for him. So anyways, so this is what Feng did. So he got this here, and then he was able to find and locate these channels. So he keeps scanning and monitoring the conductance of the device, and then what happens is this. Usually, as you squeeze, then that decreases the resistance, and then you locate a little spot like that. And then you can make a comparison between the topography and the resistance, and you can give precise coordinates of that center for people to go on and do this. So we gave the coordinates to people that do the FIB for us, somewhere in Oregon, Corvallis. They'll just slice that little area here and then look right there. Okay, so this is really, you find the switching center and you cut, and then you prepare your TM sample, and then that's what you do. So this is what we found. It's a relatively complex graph here, and this was published in Advanced Materials last year. It was a lot of work here, but to make a very long story short, what we learned when we're doing this experiment is, and I think it is illustrated better by this different type of experiment. This is an X-ray fluorescence experiment. This actually I participated. So actually this, I can say that I participated on this one, not the other ones, but this is one of the rare occasions that I actually got into the lab. So we went to Chicago to the APS light source. So we're looking at the tantalum edge at the synchrotron facility. So we took 3 turns, like we're working like 8 hours shifts, the 3 of us. Chinois, he's not here, but you all know him by his name, and Jean Paul. So we're doing that, and then this takes forever, and any temperature drift gets your sample out of the spot. So basically we created spectroscopy maps here, and then with that what we learned was this. We learned that the channel is actually composed of a tantalum-rich core and a tantalum pentoxide shell. So it's almost like a coax cable. But the resolution is very poor, but this is as good as we can get it, right? Then with EOS, you further validate that here, and then you can see, well, it looks like the profile of oxygen vacancies or oxygen, it's not that sharp. But the thing is, when you're looking at the conductivity of tantalum oxide, what you find is that it grows faster than exponential with the vacancy content. So it's really a very, very small point here that actually is contributing to the conduction. And I don't have that fully developed, but we have seen, and other people have seen, quantized conduction. So you can actually see, steps of multiple quanta. We don't see that thing about the parabolic. I have no comments on that. But we do see like one, and then all of a sudden we see 3 conduction channels. And we think that what is happening is actually you have multiple channels as opposed to one super high mobility channel. That's our understanding. But we cannot rule out the other one. Okay? So this is what we think is happening. So this is our little PowerPoint model. Now the interesting thing about the tantalum oxide is that this is the phase diagram. And so there are only 2 stable phases. You have a little bit of oxygen diffused into tantalum, or you have the pentoxide. So that gives you a very good, knob to turn. You can add oxygen atoms at will, pretty much. And for example, this is one way of doing that. What we do is the so-called current compliance, but the way that we implemented that was not with a, $100,000 piece of equipment like a B1500 Agilent. What we did was something much simpler. We got an FET. And then what we did, we controlled the current through the device with this FET. That's it. Okay, it's as simple as that. And depending on the gate voltage that we have, we can control the current that flows through the device. So this technique is very good for controlling the channel size, if you will, and the composition. The channel, as pointed out in several talks, and I tend to agree with that, is basically defined during the so-called forming process. And even though people say there are forming free, actually I think there's forming with low voltages, because you always have to create something. This idea of a very uniform conduction, I'm not so sure about that. So let me start hurrying up. So anyways, what we did was this. Different current compliances, different compositions. So let's take a further look at this. We corroborated this by, these are statistics for the different states that we get here. All right, and I asked Feng, when he first showed it, he started going sequentially, 1.5, 1.6, 1.7, 1.8 until 2. And I said, Feng, we don't know. Maybe it has to do with the order that you do this. So, but Feng never complained, so I said, okay, Feng, so this is what you're going to do. You're going to randomize this, and then you're going to do the same experiment in a random order. And let's compare with this so that we know there's no hysteresis. And that, but we got the same data. It laid right on top of everything we already had. So this is what we get, and this is an oxygen percentage that we get inside the channel. So it can vary from say 20 to 50%. Okay, so this is what we have. The way we did that was by measuring the temperature coefficient of resistance. It's a unique relationship between a composition and this number here. So I invite you to take a closer look at the paper that we sent to, it's published on ACS Nano. But the cool thing about that is actually you see a metal to insulator transition. So as you go deeper and deeper into this, it's more, if you're into transport, the term that describes the system best is Fermi glass, as defined by Mott. And the definition is this: at zero temperature, if you look at the density of states, it's finite. Okay, then you say, all right, it's a metal, but you try to measure current, nothing goes through. Why? Because you have, little beads of metallic islands that don't talk to each other. So this is the Fermi glass, and this is what we found this year. Okay, so yeah, so this is showing how we can modulate the composition. It's a very interesting paper that, I mean, interesting to me, right? that we publish, and then you can take a look, showing that we can actually modulate the conductance, and actually see, that's what I was saying in the abstract. It's a small laboratory. You can control the composition of a small nanometer size channel, and you do that with a, you know, one transistor and one device that it's relatively inexpensive to be built. So that's, I think that's a great opportunity. Now we're going to get a little bit faster here, talking about the switching speed. So I invited Antonio to join me. Antonio was a former student of mine when I was in Brazil in another life, and he was probably the best engineer that I've met, and that's why I hired him twice, once in Brazil and then another one at HP. So what I had Antonio work on was waveguides and microwaves and all sorts of cool things like that. And then when I hired him to work at HP, I said, Antonio, this is what I want you to do. I want you to create a system that we can measure as fast as we possibly can. So this is what he came up with. So he did I'll show you here. Let me just stop talking and show. So this is the setup that he built. So you have, they asked me, okay, we need a very high bandwidth oscilloscope. I said, okay, this costs $100,000. All right, so you guys have to be able to show results in the next 6 months because I don't want to get into trouble. So they worked really hard. They designed the structure, and then this is a coplanar waveguide structure. Coplanar waveguide, why? Because here's the center conductor, and this is the other boundary condition, if you will, of your waveguide. So what you're trying to do, if you're talking about like a 20 gigahertz or a 30, let's just make 30 to make it easier, you're getting a wavelength of about 1 centimeter, and you're trying to squeeze that into a few microns, like a 2 micron by 2 micron device. So what's going to happen? It's going to reflect. So this is the thing that Antonio is really good at. So he was, even though there's a little bit of reflection, he was able to do some impedance matching. Moreover, the time that it takes for the pulse to hit the sample, it's finite because we're working really fast. So you can actually measure the reflection and the transmission. And if you do that, it's almost like a 4-probe type experiment, but you do that in time. You send the pulse, and then you know what went through and how much was incident, and then you can track all those in the oscilloscope. So we created this algorithm, and okay, so here's the calculations that he did. So he said, all right, let's make sure that he makes this all impedance match, and he did all that, and this is the full wave calculation, and then he was able to show the current going through it, and then this, yeah, so you see like the level of professionalism that Antonio has. So you see that he measured, he designed, and he modeled. And model means that he has a lumped element description of the system, just in case you want to do a back of the envelope type calculation. So he understands this really, really well. So now that he understands this setup, because it's basically a setup. So first he did without the sample, the device. Then he's going to insert the device. So this procedure is called the embedding procedure. So he's just a master at that. So then, all right, so now it's time to insert your sample in here, and here it is. So now that he knows everything around your device, now you can actually measure with precision the amplitude of the signal across your device and the time. So you can measure everything for sure, and not with a regular probe station. So once he does that, and he did that 5 times, he pulsed it with a pulse generator that provided us with 100 picosecond width. And in that amount of time, he was able to switch it both on and off. So this was pretty cool. More recently, they tried, and they were able to get 85 picoseconds because we got another pulse generator. And now if you want to go faster than that, then there's an exponential price on the pulse generators as you go below 100 picoseconds. So then we can't afford. But the point is this: these guys switch much faster than most of the applications. And now here, there's this something here that is interesting. This is this is our pulse generator, which wasn't very great. So it always sent this kind of ghost peak right after it. But what I like about this is this. Here the device was on. This is the pulse to switch it off. Here's the current, the solid line is current. And then there was this ghost peak. And then you see, when you hit it with this ghost peak, there's no current. So this is almost like a pump and probe system. So in about 300 picoseconds, you can set the device, you can reset it, right? And then read it. So I think this is something that is cool about this. All right, so this is a summary. And let me hurry up, because I still have another thing that I want to show you. So you have all these very nice features about the tantalum oxide, but there's a problem. You really need nonlinear behavior. And adding a mod switch or whatever selector device in series, that is going to help us a little bit. So let me go a little bit into the details of that. I know people saw that yesterday, but let me just go briefly here. The crossbar architecture, first of all, why is that people are talking about that? Why not just, I mean, you're going from a 6F square cell size to 4F square cell. I mean, is that much of a difference? Well, let's first make the 4F square cell, and then we think about more complicated things later. More complicated things later means stacking these layers up, and then you can really decrease that number, because we're chasing density, right? Remember that that's the only thing we can do to beat flash, density. So really need to do that. So anyways, the only way to do that is by using this, because then you're not going to need any access transistors or anything. So it's very, very important that you use this geometry. But think about this. You have your device that you want to read is shorted by everything else. All these devices are shorting the device that you want to read. So or you want to write. It's even worse, writing than reading. Reading is not a big problem, because you can always create some schemes that you can actually measure that device. But writing is a big problem, because once you decide to write, you're not going to write just that one, but there's going to be some leakage. So that means you're going to have a big fat transistor to drive not only the current through the device that you want to write, but also all this parasitic. So it's no hope. So this is what happens. I'm just trying to illustrate here. You have, here's the current through the device that you want to write, and then this is just one particular current that goes adjacent to this device. And what you want is less of that current. So if you have a device that is linear like this, okay, this is very, very bad. Why? Because usually the way you bias this is that these devices here that are in parallel or in some sort of combination in parallel to the device that you have don't experience the same voltage drop across the select device. Usually they experience half that voltage. That's why they call it half select, because only half the voltage is dropped across the device that is adjacent to the device that you're selecting. So what does that mean? If you have a linear device, you know exactly how much current is going to flow through these other devices. And it's a very large current, which is, basically half the current through the device that you're selected. So this is not what you want. What you want is this. Because you see, then they're going to have this big current here. All right, so what you want is this. You want to have a device that is nonlinear, which means that at half the voltage that you write your device at, you're going to have a much, much smaller, not a factor of 2, but a factor of, say, 10 or 20 or whatever. So the idea of the select device is exactly this. Create a device or create some structure that will decrease that current so that you can barely see it like this. Still not going to solve that problem. So one way to do that, and there will be other talks about vanadium oxide. Vanadium oxide is an interesting model system for this concept. So let me just briefly go over this. It provides this so-called volatile switching. Volatile because it goes back and forth, this metal to insulated transition. So it starts at a rutile at high temperatures, and then goes to monoclinic at low temperatures, right? So that's how it goes from a metal to insulator transition. This is what the band structure looks like. So you see occupied states here, and then it's insulating, and then here you have available states. And then this is a little movie, okay? This was an intern that did this work. So he spent his summer doing this. And I think he's obviously a very clever guy, Suhas, but I think he was also lucky. Usually they say luck happens to the prepared mind, but so this is one example. So in just 3 months he was able to put all this together. So what you saw here is this vanadium oxide film that he grew, then he patterned 2 electrodes, and then what he saw was this, as he was ramping, and then he admits here that he manually synchronized. You see that the color changes, and this color change is basically an insulator to metal transition. So he was not happy about that because, as pointed out by Kito yesterday, some people think that it's a field effect driven. And and Kito also mentioned that it's a thermal effect. So this is what was done. So this is Suhas in his evenings. That's what he tried to do. He then in the morning he did that, and then in the evening he did a COMSOL simulation. So he basically had this conductivity map here that is derived from the temperature map. So he did a self-consistent calculation with a COMSOL, and basically he observes that just by flowing current through the device actually decreases the conductivity and produces that change. So this was a pretty, and then this is the curve that he obtains from it. So, all right, now this back to the the device engineering. So by chance, Genois came up with this idea. I don't know exactly how he came up with, but he was experimenting with different types of layer sequences, and one of them turned out to produce very interesting results. As you can see here, it's nonlinear on the on state, linear on the on state, short circuit and no switching, and nonlinear no switching, depending on the types of combinations that he had. But this one provided exactly the type of nonlinearity that he needed. So let's go, this came out earlier this year. So let's take a look at that. So this is the prototypical device, the device that we always make. And this is the type of device that usually lasts like 10 billion cycles. It's a platinum or some other metal that doesn't react as much with tantalum oxide, and then you have a tantalum back electrode. And then it's a great device except for the fact that it's linear on the on state, right? So, and as I pointed out, if you're looking at half the voltage, then you have half the current because it's linear in all the adjacent elements. So it's a great device except for that. So what he came up with this, he added this other layer here, and X here is a number that we don't know what it is. But the cool thing was this, all of a sudden this nonlinearity from that factor went up to a factor of 100. So basically having a very high nonlinearity gives how much you can scale your crossbar size. The higher, the bigger you can do. You don't want to make it much gigantic, very, very big, because then if you go to like a very, very small voltage that you want to read your device at, then of course, obviously, the current is going to be very small. So there's some balance. But the idea of this study was to demonstrate that using this material here, you can actually do that. But now, what does this have to do with the thing I just said about metal insulator transition? Turns out that titanium, there are some forms of titanium oxide that actually behave like that. So we don't know exactly what it is, if it's TI-203 or TI-305, but one of these, or even conceivably another ternary phase, might provide you with this so-called non-differential resistance, which is like a signature of a material that undergoes this metal to insulator phase transition. So I really like this one here. This is basically an IV curve of just this layer here, the TI layer. Okay, it's a sandwich of the titanium oxide layer. And as you can see, as you increase the temperature, you see the skink being removed. And then all of a sudden you have a ohmic device. So this is a very beautiful and simple example of that. Even cooler, I think, it's this type of behavior that you see. Whenever you have like a parasitic capacitance in a negative differential resistance device, you start to see oscillations, all right? Because what happens is this, you charge the capacitor and once you charge the capacitor, then it cools off your device, and then when the device cools off, increase the resistance, and then it discharges. So it's like you exchange energy between the capacitor and the device, you know, a heating and cooling cycle. And this is what is happening here. So you see this current oscillating here just because of this NDR effect. So this can only happen if you have a device that is truly NDR, negative differential resistance device. So this shows that you can actually use this as a select device. You get this huge nonlinearity, and it shows all the nice, interesting features. And it's titanium. Titanium is great because all fabs, it's a CMOS compatible. So this is great. So let me just wrap up by saying that.
What's the actual temperature dependence of that resistance? These IPICOs are not easy to read in your mind.
I'm sorry. This is the temperature dependence. What do you want to know here?
Well, you know.
What is the resistivity?
Yeah, what resistivity is a function of temperature.
Well, I don't know because I don't know the geometry. The resistance, we can figure out what it is, right? But the goal here of this exercise is basically to show that you go from nonlinear to linear. All right. I think it's a very interesting question, but we didn't explore that. We could spend a lot of time just trying to figure out exactly. We could take this to X-ray and RBS and figure out, oh, this is the composition and things like that. So, but at some point in time, I have to tell people to stop playing the lab and actually write the paper. So that's what I did. And because this is really what we're after. We're after a material that was CMOS compatible that could be integrated seamlessly into a fab. And
You're saying that thing shows that there is a phase transition?
yes.
How do you see? Why is not just the temperature? Why should it be a phase transition?
Oh, maybe I was not very clear. The phase transition is by Joule heating. You run current through the device. The device gets hot. Once the device gets hot, the resistance drops. And that's the phase transition that I'm talking about. It's a self-heating effect. That's right. Absolutely. That's right. But the difference, and the big difference is this. This material undergoes a structural phase transition. What that means is that you don't change monotonically and continuously as you do with any type of insulator. You have a very large change in conductivity, sometimes 1 or 2, 3 orders of magnitude at one very well-defined temperature. So you just push a little bit of current and then...
That I understand, but I don't see which is the signature of the existence of a phase transition in this compound.
Okay, well, what we're trying to infer here is from a negative differential resistance, which is shown here. The only way you can create a negative differential resistance phenomenon like this, with this a material system like this, is through a phase transition. There's no other way. It's not possible to do that. At least I don't think there's another way. You see, like, this is a constant, it's a current-controlled NDR. All right, so you push current, and then the more current that you push, the lower the resistance. What are the other systems in which this occurs? For example, the old diodes, which are PN-PN junctions. Okay, those are unipolar devices. These, I'm talking about silicon-based crystalline materials. Those exhibit that, but they exhibit for different reasons. The physics behind is different. The only physics that explains this really is a phase transition to show an NDR, a current-controlled NDR. So, just to wrap up, and then we can open up for a few questions. I think these are really exciting times because, as I said, just from a business perspective, this is not going to stop. People are not going to stop trying to find solutions for that. So I think it's a great opportunity for anyone working this field because it doesn't require like a $1 billion fab. You can just use all that existing infrastructure to create your own thing if you want. It's an enabling technology for this so-called Internet of Things because you want to have more and more memory. We all know that. We always buy computers with more and more memory. And if you want to put something that is like a data logging chip or something like that, this would be really cool to have, something that is low power and non-volatile. And you know, like I said, this is a known physics phenomenon, like a phase transition. But this is happening in real devices and at normal, I mean, human temperatures, not like millikelvin temperatures. And that we're going to be able to put that. And from a engineering perspective, this allows for the design of different types of circuits. And that, I think, Fabian is going to talk a little bit more about that tomorrow morning. And I think it's just great. Any way you look at this, I think there are opportunities. So with that, I'll just stop and acknowledge the help of everyone here that made this work possible. And I'll take your questions. Thank you.
Thank you, Gilberto. We have some time for questions, comments, criticism.
So, you mentioned VO2 and also this other material, which has a metal insular transition. So, as among other things, this VO2 is not only a structural transition, this is also a mode transition. And, there is some very dramatic change in the electronic structure that takes place. I mean, people usually just think that it's just change of the crystal lattice, but apparently this is the minor part of it. Now, can you actually think of, what I've been puzzling, my work is on metal insular transitions and not on memristors. And, part of the reason why I'm here is because I'm trying to find opportunities where the electronic rearrangements like this can have any particular role. Now, in this kind of particular situation, do you think that something more than just a change of the crystal lattice and a jump of the resistivity has any bearing on this? Because this is a complicated business, but does it, the fact that this is a really deep change in the electronic structure, does that have any relevance in this field?
Yes, I think so. Okay, let me take your question, comment, suggestion in a very practical way. Anything you can do to increase the, let's call the on-off ratio of this, or increase the low resistance to the high resistance state, it's going to be fantastic. And I think based on what you just described, like if you have other electron correlation effects, those would create a much larger, impact on this on-off ratio. So yes, I think there are lots of opportunities. Now, I mentioned and I gave the example of titanium oxide and vanadium oxide, but there are others, like for example, niobium oxide. So my colleague Matthew, he published also a paper on vanadium oxide, and I think there was a question yesterday from you, like how long does it take for that transition to take place? So in his paper, what he showed was like he did use the same setup, like this high speed setup, and then he was able to show like 500 picoseconds or something like that. But I think it's more like a thermal effect than actually the phase transition. The phase transition actually it's faster than that. So I think it's really cool to be able to see these oxides showing these phase transitions at elevated temperatures, meaning above room temperature, because it's really that you can really use this. And some people say, like for example, with the niobium oxide, the curious thing about niobium oxide is that the phase transition temperature is not 65 like this case, or like a vanadium, right? Or it's not. Let me show this. I always forget. I don't know what the temperature is. I don't know. Let's call this 200. It's not 200, but it's like 800 C. But you think about, I'm heating my niobium dioxide device at 800 C at a very small spot. But it's it's amazing that you can actually have a device that is 800 C in your lab, in your probe station. But it's a tiny little part of it that is 800 C that is actually in the metallic phase. So.
You want to use gloves?
Sorry, no. I mean you just, but it's.
So there was this talk of, is this working?
Yeah.
But how you have to have a phase transition for thermal breakdown to occur. But and I certainly
sense in vanadium oxide that's happening. There is a phase transition. But like the theory of like thermal breakdown, was originally developed decades ago, which is activated system. So you can have thermal breakdown if you just have an exponential dependence on the temperature. You don't need to have a whole phase transition. And so I mean, with the graph, there's no sharp transition that I can see in that particular graph with the temperature. So I mean, if you imagine that from Newton's law of cooling, as your temperature increases, your cooling rate goes linearly, but your joule heating increases with voltage. The intersection.
Look, the thing is, you see, this here is a 2-probe measurement, okay? What I'm saying here with this graph is that it goes from nonlinear to linear, right? And also, you have to understand that there's lots of series elements that are masquerading what you're asking for, both of you. Okay, so that's based on what I'm trying to say. Is it possible to see, sharp transitions and whatnot? It is, certainly. But this is not the structure to do that. We have done that, but this is not it. So, growing exponentially, that happens for any insulator, but that's not the case here.